To give you a little bit of a notion of sort of frequency and time, et cetera, and pretty soon we're going to throw time away because we're only going to be interested in space, but since you talk about how quickly something wiggles, and it originally was derived from one dimension, we'll talk about it this way. So here I have a signal, okay, g of t, okay, that's made up of two parts, okay. It's got a sinusoid of some frequency f, and then another sinusoid of 3f, but it's been scaled to make a third. So that's this signal here, and you can write that as just the sum of these two sinusoids. After all, that's what this equation says. And because of linearity, the stuff just sums, the combination of the two on the right gives you on the left. And if I were to draw out sort of the contributions of the sinusoids to the signal, it would look like this. Okay, so this is written in this particular way. I'm only showing you positive frequency. We'll talk about negative in just a minute. But whatever f is, the idea is that the signal here has a frequency spectrum with a certain amount of power at f and sort of 1/3 of that at 3f. Okay, and this is one form of drawing out the spectrum. We'll talk more about spectra in just a minute. You'll notice that this picture on the left is sort of kind of approximating getting towards a square wave. And it turns out that actually, if you really wanted a square wave, what you do is you keep adding these odd frequencies, all right? And I want to show you this because sometimes people will ask, well, how can I get sort of a sharp boundary using just smooth sinusoids? So here we have our original picture, and now I take that original one and I add in something that wiggles at 5 times f, and you see that I'm getting closer yet to a square wave. And then I get to 7 times f, and what comes after 7? 9. And what you can see is that we're getting closer and closer to having this as a perfect square wave. Okay? And in fact, you can show that a square wave can just be written as this infinite sum, okay, of these frequencies. Okay? And the amount of power you need goes down as the frequency increases. All right? So what we want to do is we want to get to a point where we can look at a signal and say, process it in a certain way or compute with it in a certain way to say, what are the sinusoidal components that go into making up this image? And in fact, you can show that to do a square wave like this, you need an infinite sum of decreasing amount of increasing frequency, and that's what's shown here. Now, what I haven't done is I haven't talked to you at all about phase. And in fact, I'm not talking at all about, you know, what the phase, right? I could have this offset or I could have different elements offset. And in fact, all I'm showing you here is the amount, or you can think of it as the power, we'll talk more about that in a minute, of the content of each sinusoid. And the reason we're not talking about phase is our goal is not to reconstruct an image. We just want to, typically what we're going to want to know is how much power there is in each of the different frequencies. In computer vision, we're interested in sort of analyzing what's going on. If we're actually going to reconstruct images, then we would probably have to worry more about the phase to get you better reconstruction. But we're not going to do that today.